Hello developers, let's start developing. My name is Veko, and since we solved all of the Advent of Code 2021 tasks, we're gonna take a look at some of them that were a bit slowish. So first we're gonna focus on task 19. That's by far the slowest implementation that we have. So I will just run it for my whole dataset, and you can see that this thing runs and runs and runs. Those remaining number needs to get to 0. So I know that we're making progress, and we're running and we're running and we're running. And this will take approximately 10 minutes. That we're not gonna sit through that because we already know it gives us the correct answer. Yep, the answer was 425. Maybe we would have gotten the same answer faster by just guessing, but who knows? Yeah. So, how do we optimize this thing? Let's look at the solution. Let's see what part 1 actually does. Part 1 and part 2 are basically identical, so we're using the same thing twice. We're setting up the first beacon as a reference, and then we're building up the reference array, and we're adding to it and adding to it and adding to it, while we don't get to a point where we don't have anything more to add. So, in essence, each of these runs of these, we have a while loop, and then we have a for loop, and then we have a for loop, and then we have a for loop, and so on and so forth. So we have a lot of things that are going on that I feel that are data intensive. And let me just check if I have my performer class here. No, I might need to switch on another branch. Let's just stash what we have. Yeah, day 19. I'm quite sure that I'm supposed to have a file called priority profile performer here. Not got git. Day 21, day 25. Yep, this thing. Yeah, let's just copy it over to master, because I don't want to get the branch, but and this is not how you usually want to do merges, but it gets the job done. So this is a very simple class that will enable us to do some performance analysis. So we have a start point where we are executing the performance now call, which is imported from the perf hooks module, which is native to Node. And when we're calling the end, we're again calling performance now, getting their difference and adding it to the existing value. So this way, if we keep and I wanted to have another method, clear of name, which will be a T, and we will basically this dot values dot name and this dot starts dot name. So we will clear it if we need to. What this enables me to do is to have cumulative performance analytic, because we have some loops here and each iteration of the loop is relatively fast. So if we are just measuring the iteration of a single loop, everything will be just as fast. So if we say start equals performance dot now, and we usually want to include performance, something like this. If we run this, first of all, we're gonna get a lot of output, because on of each run we were gonna get some kind of a something. What are we doing wrong? We just added that one and that one. And we need to pop our stash, because we're executing actually day 23 and we need to run day 19. So we're getting lots and lots and lots of times, and we're not getting any meaningful data from it. So that's not what we want to do. We want to measure piecemeal but cumulative. So I have one inkling that this might be a bit on the slow side. Specifically this. This is kinda calculating all the beacon differences. So I will create P as a new performer. And let's have it of string. Actually, I want to use this so I can limit the types of metrics that I want to say, and that will be basically get diffs. So now I can say here, well, p dot start of get diffs, and here I will say p dot stop. And this is a good behavior that actually GitHub Copilot did, because my performer class does a bit of a stupid thing. If we are starting something, we should not end it. That's a bad name. If we start something, we should stop it. So this should be called stop. And then we can have a variable also called stop. If we have a method called end, that means that we need to have a method called begin. So, but I will use the start stop paradigm, because that kind of feels like we're having a stopwatch and we're starting it and stopping it and starting it and stopping it, and so on and so forth. And now I can just say here console.log p.get values, and this actually returns an array. Okay, I'm fine with that. And I will limit the run of this. So I don't want this thing to run while we have data. I want this thing to run only some of the time. So let's say while res.length is bigger than 27. Yeah, we will get the wrong answer, but we don't care about that. We just need to see what percentage of time is actually taken up by our getDiffs method. At the moment, I know that the while loop is slow as a whole. application is slow, but I have no idea what part of it is slow. So we should find the 28 and then we should stop, if I'm correct. And I will put in 28 here. No, let's leave 27. We got some behavior that we started getting slower and slower. At 27, and I will just comment out the part 2, which is optional anyway. So we don't run the same thing twice. Part 2, as I said, is 99% identical to part 1. Actually, we're getting a slowdown for 29 already, so maybe we can put in larger than 28. So this is not it, because our getDiffs method is spending about 101 milliseconds out of our 27,000. Okay, next candidate. And I will actually leave this in place. So let's see what we are doing else. So after we're getting the diffs, we are grouping them. This is part 2 we're looking at. After we get the diffs, we want to take a look at every rotation. So after we get the diffs, we are grouping them. And after we get, we need it like this. Those are separate strings. After we group them, we're taking the one, then we're translating them. That should be fast. That's another operation that we are doing. And after we translate them, and I actually reference map, so we're mapping everything to keys, getting ref keys, and then we are checking ref keys. So get ref key, check ref key, and after that we can dive within these if we want to. So p.start group, and we can, if we throw an error, no, actually we cannot do that. We need to do this here because I'm not concerned that this is slow, or this, and we're gonna do a p.start translate, we're gonna do p.end, p.stop translate, p.start get ref key, p.stop get ref key, p.start check ref key, and this for loop. Let's put in the splice. I don't think the splice is that slow, but it could be on a large array. But on the other hand, this is a 30 items array. So that's not gonna be the problem unless I'm mistaken. So let's run this thing again and see what values we have now. So what I want to mention is we don't need to optimize at any cost. There's a lot of talk, especially in university, about O of n of this, O of n squared of that, O of n log of n, but in real life that's mostly unimportant. For example, if I have, because in theory, we have our winner. In theory, the n goes from 0 or 1 to infinity and so on, but in real life that doesn't happen. We need to know the scale of our possible n's. For example, if I have I don't know, some kind of algorithm that calculates some interstate things for the USA. So it depends on the number of states. Let's say I have a very simple and very nice algorithm that runs in O of n squared. And it takes about 2 minutes to run it, and I run it once a month to calculate, I don't know, tax percentages, interstate tax percentages. And it will be an O of n squared algorithm, but there are only 50 states, and it runs in 5 seconds, and it runs once a month. And that n is not likely to change. I mean, DC could get statehood, you can accept Puerto Rico or Guam or I don't know what, but there will be a long time before that n becomes something like 200, 300, if ever. Most likely by the end of this century, the 21st century, we will have something like 56 states if we're optimistic. And that will be about it. And it's quite possible that there will be exactly 50 states. So, not caring about history, about politics too much, it's sometimes in a real world scenario, it's not important if an algorithm is n squared or x to the n or 2 to the n or even n factorial. If it gets the job done and if we are reasonably sure that that n won't skyrocket. But that means it's on us as a developer to correctly estimate the n. If we say that n will be 30-ish, that means it's okay if we get to a 45, but it's not okay if we get to 6,000. So then we might have an algorithm problem, and we may need to change it with a better one, with an n log n or n O of n or even O of 1 algorithm. That's okay. But usually the first 3 rules of performance, as I call them, are measure, measure, and measure. So you need to measure and estimate your data and test it and see it, and only then you will get to optimize what actually needs to be optimized. And what I'm speaking about is actually a very nice example. I have no idea where I'm pointing it. No, I'm pointing to the other way. Over there, you can see that basically all of my assumptions about which part is slow were incorrect. You can see that getDiff actually uses let's calculate, that's 90 milliseconds divided to 27,206 multiplied by 100. So our getDiffs method that I thought would be slow takes about 0.33% of the runtime. And the translation takes way less, the getref key takes way less, the checkref key takes way less, and the group, which I thought would be trivial, and which I'm surprised about, and I have no idea what is happening, takes, 853 divided to 27,206. This is not an exact percentage, but it takes about 98% of our runtime is spent grouping stuff. So if we manage to speed that up, then we will have a speed up. So if I didn't do this, if I didn't measure, and I just went off my hunch, and don't forget, I have a lot of experience, so my hunches are usually based on lots and lots of experience. But I have even more than that. I have knowledge that hunches in performance tuning are irrelevant. Measure it. Of course, measure the best and measure first the part where you do have the hunch. But measure and see and get specific numbers. Because right now we have this. So what would have happened if I just went off and said, oh, getDiff is terribly slow, and I sped this thing to a percent of its runtime. So I did lots of work and lots of refactoring, and I invent some new creative data structures, and I do a lot of things, and get diffs is 100 times faster than it used to be. I will move this from 89, I will move this from 0.3% to 0.0003%, which is not a speed up that anybody will brag about. Yeah, that's basically statistical noise. That's basically whether we're running hot or cold, whether there's network traffic on my computer at the moment. We're moving into microsecond category, and that's just me. So if I went with my hunches, we would have spent a lot of time optimizing something that, to be honest, did not need optimizing. It was fast enough. Yeah, it's a nested form. One of the least optimal structures that we have, that can be at all. But it's fast enough. And on the other hand, here we have a pretty little method where we're calling group and then we're calling filter and this takes 98% of our runtime. And of course, group by is one of my methods, and I think I have an inkling what the issue might be. Yeah, so we're using some kind of we're hitting, I guess, some kind of a performance cliff when we're using too much memory. So, in general, what are we doing? What does group by do? Because I've used this method quite a lot and it's usually quite fast. For each item, we have the index and the number. We are defining a new array, and then for each array, we are doing a find. This could be slow if we have lots of methods. And if the key item doesn't exist, push it, otherwise this is fastish, so to say, and we won't have too many items. So I guess, and we have a key equality method which we are not using. It uses the default. Yeah, whether two keys are equal, basically compare the first one with the second one. And what do we use as a key? We use to key. I don't think this is the problem, but how can I be sure? One way to find out, and actually that means that I will have to, in order to use it in this method, I will have to define this as a global variable, but that's not a problem, and this we will change this into this. P dot start, we need to add a counter. Just start to key and end to key. This is the result and return result. So maybe there's some weird stuff in our to key handling, and that is actually the thing that is slow. I don't think it is. Where is to key? Ah, here, that's to key. So actually we are spending quite a lot of time, almost a second, executing to key. So maybe we're not that slow, we are just calling it too many times. Okay, but that's a data point that we might want to look at after that. But for now, what I will do, I will more or less copy this logic over to the day 19 so that we can work on it. Because we have now diffs that we want to group by the diffs key. Can we do that in some other way? How do we group? And we only need them. Only need the key. Instead of that, let's try something else. Let's try to implement the logic of this. So we can have const, if we have only, are we using the diffs after that, group length, grouped items of 0. And do we need the item of 0? Actually not that much. We can have here another structure that's not, that we just need the scanner diff. What are the diffs? The diffs are the difference in x, y, and z. And then we move off that. Do we have a class for x, y, and z? Yeah, we have it, we call it point. So if we want to have diffs like that, for now we have diffs is an array of point. And we need to do something, and here I will use something that I like very much, and that is called a Schwartzian transform. And of course I'm gonna have to Google how do you spell that. It's spelled like that. And this is just as an idea. And we're gonna take each diff and we're gonna map each diff to a tuple that has the diff and the diff key of diff. And let's have the key first. Let's have the key second. And now, because I want to have all the diffs sorted, but I want to have them sorted by key. And if I just do this, and let's expound, let's have a other video that where I will use this to explain why we actually need the Schwartz. And now we can just sort on the second item of this thing. So if we have, yeah, this A with an A key, B and B key, basically sort on bk dot log. Bk is a string, so this, what is inferred? Let me just see. Yeah, this is an array of arrays of string or points. No, this is actually a tuple of map to an array to a tuple that has a point and a string. Yep. So now the Schwartzian is an array of point string tuples, which means when I do a sort like this thing should know that bk has to be a string. Yeah, which means that I can do then local compare with ak. Actually the other way around, because I don't really care as long as they are sorted by key, but I think it will be better if we are actually sorting it by in a normal order descending. So now for the second part we are just basically getting rid of the key because we don't really need it. So we calculated the Schwartz, the key here is the Schwartz, then we sorted on the Schwartz, and we can use this and this, and let's leave it as A and B. Actually we need to call them we can call them underscore A and underscore B, so everybody is happy. So we got the sorted diffs. Do we actually need the... Yeah, let's keep the key. Let's keep the key. And now we have the diffs, and they are sorted, and each of them has the key. And note that when we did that, we only called the key method once on each diff, and we can have a lot of diffs. So once we solved that, we got that, now we need to actually group them. And now grouping them can be done easier. We know that we all have at least one diff, so this cannot be an empty array. If it's an empty array, we did something very, very wrong. So we can say, yeah, we can add the first one. Group will have a key, which will be that thing. Yep. But to be on the clearer side, let's just do this. So the key is the first item, and the diffs is an array which has the actual value of the diff. And now we can run a loop, a regular for loop, for index of sorted key diffs.length, and we can destructure it into a key and a diff. And we're gonna start not from 0 because we already processed 0 explicitly. We're gonna start from 1. So because the diffs are sorted, yeah, we can take the last thing and we can check whether the key of the last is equal to the key. So what is the key of the last one? It should be a string, and the key is a point. Ooh, yeah. We need to do it this way. Thanks, TypeScript. So if our key is equal to the last key, and actually we don't need the diffs themselves, we need just a single diff, because if the key is the same, the diff is the same. And we're gonna need a count, and that's gonna be 1. So if Our key is the same as the last key, and actually we don't need to do this each time. We can just say const or let current is equal to group of 0. We don't need this, and we can just say if the key of the current is equal to the key of the next one, then all we need to do is increase current count by 1. If it's not, I guess it will, yep, but I will do it the other way around. Current equals that thing, and then we're gonna push the current in. So now each time we change the current, we change the count of the current, it automatically gets updated. So right now we have something like that, and we can now just say because we have this thing as well, grouped equals, we don't need to sort anything, we need to filter where group.count is bigger than or equal to 12. And since group has a bit of a different structure right now, we are not getting items of 0, we just need to get diff. Let's see if this custom built grouping algorithm, because this is a generic grouping algorithm, it works just fine, but it's not optimized for anything. It basically we can group things that are not even sortable. We have a key selector, we have a key equality, we can do group whatever we want, however we want. Here we are grouping specific things, so we know more than the generic method. Generic methods are great, but they don't always have deep knowledge of our data. And we do. So I changed the generic algorithm with a pretty much custom one. It still might not be optimal, but I think it might be better than the one we have. Actually, I have no idea. And there's one sure way to find out. Seems to be running faster. 5 seconds. So this thing was half a minute and it's now 5 seconds, which means it's a lot faster. It's 6 times faster. Just for the fun of it, let's see. Will we have a marked slowdown? Now it might make sense to actually run this thing through everything and see if it has any issues, so on as it goes. Yeah, I definitely feel a slowdown. As we should. This is in basically quadratic by line. So each line, each 2284 and 89 gets slower and slower the further on we go. But we managed to get everything done in 32 seconds, and 31 seconds out of that was spent grouping everything. And 3 seconds out of that was spent in getting keys. Where are we calling and why is that thing that slow? We're getting the keys here, we're getting the keys here. How many times are we calling to key? Let's do another thing. Yep. Maybe we have an extremely fast method that we're calling an extreme number of times. Yeah, that would have been nice if we had on the performer a call count as well. That might not be a bad idea, but we haven't implemented it so far. Anyway, we got to a point where basically running the whole input is not unfeasible. We have 30 seconds runtime, so while not too interesting or dynamic, it's possible. The 10-minute things was too large. We would have to basically take a smoke break or make a coffee each time we are doing anything. And as I already described, this is by nature a relatively slow algorithm because we're just meshing everything together. We called it about a lot of times. 10 million times. Do we have 10 million different things we can call it with? For example, how many diffs there are? Why is this written that many times for each loop? So we're taking our target. Yeah, we are running through each rotation of the target. Yeah, we have 24 runs for each rotation. This could be slow as well, and you see it's innocuous. That actually hides a method call. So let's measure that one as well. And let's remove this, but on the other hand, just a second. Yeah, let's remove that one, but on each run we are running this thing. Let's look at the data, because while we're counting all the rotations, the ref keys stay the same because the reference stays the same. That's what we're trying to do. We're trying to match any rotation with the current reference. So basically if we move this before the parenthesis, before the for loop where we're running the rotation, we will speed this part up 24 times because we won't be doing it 24 times, one per each possible rotation. We will just do it once, and that's like we're gonna save 5 milliseconds because one will stay. Yeah, so that is an optimization that we can do and that we will do, but it will do nothing for our speed. Yeah, we can just get the target and get the ref keys here, because for each of these for loops that stays the same. And let's see if I'm correct. Yep, I am. No, I'm not. Now it says that get ref key actually took 15 milliseconds. Who knows? Anyway, as you can see, this one is a large one and this one is a large one. There's some is more than that, but it seems that we have a lot of sorted keys. Actually, now that we're here, let's try to break this a bit more further. So it's not the whole grouping. Within the grouping, let's do the sort. And of course, since I want this to be a bit on the formal side, let's do it like this. We can have group sort, and then we're gonna have what? Group match, and then we're gonna have group filter. And in that case, we don't actually need group, because group is gonna kind of be the sum of that. So we have group sort, so stop the group sort, p.start start the group match, start the group filter, and stop the group match, stop the group filter that we don't need. So, group sort, group match, group filter. Well, I guess we're screwed. The slow part of this is group sort. And there's just no way to do group sort faster than that. Not that I can think of. On the other hand, this does to have two parts. And this is the Schwartz. And then we can do sort on the Schwartz. Not you, but you. So we're gonna have group map. We're gonna have group map and group sort. Let's see which one of these is actually the slow one. Yep, group sort is the slow one. That takes the lion's share. And you can see that just because we moved some stuff around, we actually changed the number that time is called and it actually increased. Who knew? Oh, just a sec, I think no. No, I was wrong. So what would happen, because I have an inkling. This is a comparison of strings. Comparison of strings. Let's see what the keys are. And since we're here, let's use this method to run a quick and dirty analysis. And I will use minus number dot infinity. Actually, I think there is this thing. So on this run, this will run much slower because I want to calculate something, but I have a feeling that might prove correct and might prove an idiotic idea, so I am not gonna say it because before I get to see it, but let's just say that if point dot x is, this need to be the other way around. So our maximum is at negative, at minimum is at positive, 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 negative, negative. So if our point is below the minimum, then it's the minimum. Is before the maximum, then it's the maximum, and I'm hoping that Copilot will totally write all of this code for me. Because I know what I want to say, you know what I want to say, and I guess Copilot knows what I want to say. Let's just console log ranges. So we will get the total range where our points lie. We will get the minimum and the maximum value that they were called with. And of course, this version will run a bit slower than usual because we're gonna be calling those ifs about 1 million times. About 10 million times. Z doesn't have a maximum? Oh, Copilot, you messed up something. Yeah, its maximum is negative infinity. If point.z is bigger than the maximum, is less than the minimum, and the minimum six of these. I need 6 of these, and I had 5. 1, 2, 3, 4, 5, 6. Yeah, we didn't get that because we didn't use it. So these are the minimal and the maximal values. Which means that if I add, for example, 1, 1, 1, 1, 1 to each of these, I will get some positive number. And of course, if I add that same thing here, I will get another positive numbers. And what happens if I multiply this one by, let's say, 15,000, and then add this one and multiply this thing by 15,000 and add this one. I got a 13-digit number. And that number is guaranteed to be actually exactly representable in JavaScript. And these three are actually, and those are the maximum values that we can have, these three can be looked as digit in a number with a base of 15,000. What happens if I don't use 111 but use 15,000? Let's not use too many constants, let's reuse that one. Yeah, we get, oh, then we cannot use 15,000, we will have to use 20 here. Actually, you know what, let's lose 12,000 as the number, and the numbers we're getting are bigger than 15. So we're going to use 11,000. Because if you have a, let's say, something in a base 16, you cannot have a digit that is bigger than 16. Just like if you have something in base 10, the regular one, you cannot have anything that's in, you cannot have a digit be 11. Because it just cannot be. Digits can be from 0 to 9. So in a numeric system with base 15,000, digits can be from 0 to 14,999. But anyway, this means that we can refactor something. Let's remove this, we don't need it, because the key is something that we need to be unique for each point. So we need some part somehow to translate a point to something that is primitive in JavaScript, and that is usually a string, and that I've been using, but we can also use a number. We cannot use a boolean because there are only two of them. So if we say that the result is not this, but the result is point of x plus 11, let's use this const offset, that's 11,000, and this basically guarantees that what we have is positive, and const base, which is 15,000. So this is point plus offset times base plus point y plus offset. Also, we cannot have negative digits. The digits are always positive. So this whole thing needs to be done times base, and then we add point z plus offset. So yeah, let's have the result be that. So now we, instead of moving it to a number, we are moving each point to a, well, instead of moving each point to a string, we are moving each point to a number. You can see that the algorithm is a little more convoluted, but basically it's unique still, and that's the only thing that we needed. Now that's gonna be a number, and we cannot do a number compare, but we can do this kind of compare numbers. So it's quite possible that this will be much slower than what we have, but one way to find out. The previous results were these. The execution of toKey method took 3 seconds, and the execution of the sort method took 23 seconds. And note that when we executed the group map, that's when most of the toKey calls were done. So I think that we will be exchanging some of this time for this time. So we will increase this time and decrease this. And that's what I'm hoping to see. But one way to find out. Is it me, or did this thing go whoosh? So let's see what we have. So our total runtime is 10 seconds. we actually reduced the to key time, and you can see that we have the exact same amount of calls. So working with numbers is almost always much faster than working with strings. So that simple string that we had executed twice as slow as this monstrosity. And what's more, if we do this, it might be even a bit faster. Getref key was, yeah, getref key went down because we're using the new to key. Rotate stayed about the same. Get diffs stayed about the same. Group map went down from 6 to 4.5. And that's all because we have a more efficient to key method. We didn't change anything in group map except the to key implementation. And group sort went from 23 to 4. From comparing strings to comparing numbers. And group match, I think, went down because we're again not comparing strings on this line, we are comparing numbers, and numbers are much more easier to compare. The rest of them are about the same. Check Rifki also went down because again we're checking whether that includes that. We can, for example, we can make it so that the ref keys are not an array, but they are some kind of a hash map, and we are just using a lookup, which will be much faster. But again, the whole check ref keys, we have get ref keys there and check ref keys, and those together last less than 20 milliseconds. We're not gonna worry about that. Anyway, I have an idea. I have a feeling that we got about to the limits of what this algorithm, because again, this is a really bad algorithm, what this algorithm can do. So unless we change the way that we are processing and building up the reference, I will leave it like this. Let's just try to run it without all this profiling. Because one thing that you need to remember, profiling slows things down. So this will be faster when I don't have all those performance now calls. Because each of these is a performance now call. I will comment them out first and see what happens later. So comment this out, comment this out. Don't need this. Let's leave that single console log there. Found a match. Log the translate. Check ref key. I think that's about it, and we just don't need this output. Let's run it as a real program. Yeah, it still gets slower and slower, but with 6 seconds I think that I can live. Especially that I'm gonna remove, I am allowed to remove this, because otherwise before that we would we would have nothing to look at for 30 seconds or something like that. We can wait on this stage 6 seconds, but 30 seconds is a bit much. And the result part 1 is 425. Yeah, let's have the same algorithm now for part 2. Yeah, part 2 has exactly the same thing, and it has another part after that. Do we do something with index? Yeah, we have index as well. I think that we should be able just to do this. If we're not, something will break and it will not hesitate to tell us. Let's see what we are supposed to get. We are supposed to get 13,354. And we are supposed to include part 2, otherwise, of course, it won't run. Part 1 done. Part 2 is 0 because we didn't do something that needed doing. Let's see what we're doing here. Scanners. What is scanners? Scanners push, scanner diff. Yeah, we need that line. And I don't think that we have it in this one. Yeah, we're using scanner diff and then just we throw it away. That needs to be before the splice. Yeah. And while I'm here, I will get rid of all of these. Maybe we'll need to optimize something more. But when we do, we will just reinsert them. In a regular program, this would be all under a debug directive so that they are not included in the build when we are using it, but well, this is just some code that we are playing around with. Do we have something else commented? Yeah, this thing, and this thing, and this thing, and now we can just do this. Looks weird, but it works. So, as we said, let's copy and paste this, and we need to say scanners dot yeah, put the scanner diff in scanners. Let's see if we are getting the correct result, which should be 13,354. How? Oh, I undid once more. That's the correct value, and it took even faster than the first time, and that's great because this means that I can do the thing that I was talking about run all. I can actually include task 19 into my complete run of all the issues in 2021's advent of code. It won't be the fastest one, but I don't think that it will be the slowest one either. So task 12 we're waiting on, task 18 we're waiting on, task 19, the one we did, we're waiting on. Task 22, 23, and I think 25. 23 is a ridiculously slow algorithm, yeah. And usually the second part went faster, yeah, 12 seconds. And 25, I think that we're hitting again some performance cliff with task 25. Maybe we can optimize that as well. And here it is, a full spectrum of what we're doing. So we can see that task 23 takes 51% of the time, task 25 took 19%, and the one that we use it with the naive algorithm, but nicely optimized, takes 18%. So it's the third slowest, so to say. And our total runtime is just over a minute, 69 seconds. So that means that we need to shave 9 seconds off somewhere, and I guess this is the most likely candidate, as it took 36 whole seconds out of this 69. So that's my optimization of task 19. I will commit both the original and the updated versions to GitHub. You can take a look at them and compare what I did and why I did it, and keep developing.